So the second problem is going to be a lubrication problem, and now I've purposely chosen two very different lubrication problems, and usually you will have one or the other. You know, in this first case, essentially you impose the geometry of the film, right? And then you're trying to get to the forces. Oftentimes you don't impose the geometry of the films. Oftentimes you have a thin film which flows. Because you're spinning it, or because it's just you just rolled your paint, and now you have a thin film, and you're interested in the shape of the film. So you're not imposing the shape. The shape is actually this H, is what you want, and those are more typical for lubrication problems. And usually, you will not know what the thickness of your film is. So let's start with our second problem is paint layer, but you would have similar problems with any kind of coatings. And we'll just assume that we have a vertical wall to make the geometry simpler. Of course, I invite you to see what happens if your wall is slightly tilted. You know, if it's completely flat, it's not going to be really interesting. If the wall is on top, then you have to know something about stability analysis, so it will be too difficult. But for this wall, for a wall at 45 degrees or at 30 degrees, everything is almost the same, but there are little differences. So I invite you to do that. Now let's assume that we start from a thin layer of paint. So you just pass your roller on top of your wall. It's a liquid. It's paint. I don't know what the viscosity of paint is, and you should look it up on the internet, but it's more than water. It's probably close to oil, right? So it will be an order to 2 orders of magnitude the dynamic viscosity, and larger than water. So water is 10 to the minus 3. Paint, I would say probably 10 to the minus 1, maybe on the order of 1, something like that. And the question is, we'll look at the height. What happens to the height of the gap? What sets this height of the gap here? Right. So that is our question. Now, even just from the beginning, this is a small layer of paint, but which way is the flow going to go? Downwards. Like, is it going to flow really quickly? Your experience with paint is that you just paint and then whoosh, it's all on the floor? No. Why? Because it's viscous, because it's only a small layer. Yeah. Now, I've had this at exams, right? What is driving the flow downwards? Gravity, right? So it happens in exam. 60% of the students then write the lubrication equation and cross out the gravity term, and then you have a problem because nothing drives the flow. And now you laugh, but after the exam, while I grade, I don't laugh. Right? Because the problem starts like this. You just crossed out the reason why there is flow, and of course, right, were it not at an exam, you would have known not to cross that out. But during an exam, for some reason, you just shut off your brain and you just start crossing terms, because in the last example you did, there was no gravity. No, you really have to just take a step back. Just like, what is driving the flow? It's going to flow down. So make sure that when you write your equation, at least you always get the flow in the right direction, and it's going to be due to gravity. So don't cross out gravity. Yeah. So and then the problem is quite easy. Yeah? So it's an interesting little. There's some interesting physics at the end which I want to discuss, but you essentially have your mass conservation equation, right? I'm going to write directly the lubrication version of the mass conservation equation. Now, in this case, a priori, do we have a steady state? A priori, we don't have a steady state. You actually don't know really what happens, and if what we're investigating is the formation of those little droplets, which are annoying. When you paint, then all of a sudden you see those things, and then you have to paint over again. You're like, then it's going to be unsteady, right? Because this is a very unsteady phenomenon. Those things appear, so it's not steady. So at this point, we're not assuming a steady state. And then we have the x and the y momentum equation. Now either you flip all of your axes, right? But if you want to, if you want, at this point, I would encourage you to be a bit flexible, and I would pick this, right? Does that make sense to you? Because then we just essentially keep on saying the x direction is the flow direction, and the y direction is the direction across the flow. So that would be a choice which would help you if you directly flip your axis such that you're using the same equations that you're used to. Then it's going to be easier. Okay, so in that case, the momentum equation then, in the x direction, I have minus partial p over partial x plus mu times the second partial of u with respect to y. And here, do I have a body force? Yes. And this is what is driving the flow. Okay. Now, if x is pointing downwards, do I have a plus rho g or a minus rho g? A plus rho g. Yeah. So here I have plus rho g. And in the y direction, I have partial p over partial y. Do I have a body force? No. Now, this is very generic for lubrication. When you have a lubrication flow, oftentimes the pressure, with a boundary like this, the pressure is what is easy to get, and the velocity is a bit harder, but also easy to get. Okay? The pressure here is easy to get because we get from this equation that the pressure is going to be a constant which only depends on x and possibly time. Yeah? Now, in that case, what is the pressure? I think you already answered the question, but in that case, what is the pressure inside of the film? Why is it atmospheric pressure? What do you use? What concept do you use? What concept do you use to say that it's atmospheric pressure everywhere? Actually, you're right. Huh? This is the one thing which I didn't say. When you say the pressure is the same, we are assuming that the curvature is going to be really small. Right? So what you have to impose now to get to the pressure is the boundary condition. Right? And remember that to get the pressure jump, to get to the pressure, you impose the boundary condition in the normal direction. So you're writing a stress balance at the boundary in the normal direction. And remember that we had that delta P is equal to the surface tension divided by, if you have a sphere, times the average curvature, right? So if we assume, and I would want to see that in exam, if we assume, and which is true, right, if you think about your layer of paint, how much curvature do you have? Very little, right? Your interface is mostly flat. So if your interface is mostly flat, then your radius of curvature is enormous, it's almost infinity, and therefore this term here is close to zero, right? In which case, what is the pressure jump at the interface? Zero, right? So from this equation, you get that the pressure is not going to change in this direction across the film. Right? So here, P equals to, is only a function of x, so it's constant at constant x. And then I go to the interface to identify my pressure at this height. And what is my pressure here? It's atmospheric pressure. Right? Now, if my pressure outside of this film was not atmospheric pressure, say I'm underwater, for instance, and there is a hydrostatic pressure term, then I would identify with the hydrostatic pressure term. Yeah? So you have to identify the pressure right here. So you're putting yourself at every single x. At every single constant x, I know that my pressure is not a function of y. So what is my pressure? I go to the interface. Right? Do I have a sharp curvature? Do I have surface tension effect? No, because my interface is almost flat. And therefore the pressure in the liquid phase here is the same as the pressure in the other gas and fluid phase here, so it's atmospheric pressure. Is that clear? Yeah? Okay. So from here, we use the boundary condition, which is a stress condition in the normal direction, to identify the pressure. So let me write that really quickly. So I have P, then at X, and you can write Y equals to H of X. Right, so this is the pressure at the interface. Minus P atmospheric, which is equal to sigma times the average curvature, and this here is equal to 0 because the interface is almost flat. Okay? So we have that pressure at any x and at any y inside our film is equal to P atmospheric. Yeah? So what about minus partial P over partial x? 0. Yeah? And so from there you see directly your flow is not driven by a change in pressure inside of the film, because the pressure inside of the film is the same everywhere. Right? So if you had crossed out the rho g term, then at this point you have nothing to drive your flow, which is what would happen if you were in the space station and you just paint. There is no gravity to pull anything. You just your layer of paint remains a layer of paint. The only thing that can happen are surface tension effects. Right? But if it's very viscous, then you might not see, the paint might dry before you see anything. Okay, so here P is atmospheric pressure, so in particular partial P over partial X is going to be equal to 0. The flow is not driven by a pressure change, which was your intuition to say that the flow is driven by gravity. Yeah? So the gravity term is the only term that we have left. Okay, so now we're left with the x momentum equation, and our x momentum equation is second partial of u with respect to y is equal to 1 divided by mu times, sorry, minus 1 divided by mu times rho g. Yeah? Yes. Okay? So what do I do here? This is similar to what we had before. Very standard in when you're facing a problem in lubrication. What do? You integrate over y. You integrate over y to get to q, because then you want to take your x momentum equation and put it into the mass conservation equation. And the mass conservation equation has this q. Right? So now that you know what the velocity profile is, you can express what the volumetric flow rate is. Right? So you want to get to q. Right? You want to get to q because q is the integral from 0 to h. You don't know what h is, times u dy. So you need to know what y is. What is y? And so to do that, you integrate the x momentum equation. Right? You have to integrate how many times? Is this not a trick question? You have to integrate how many times? Twice. So you need two boundary conditions, which are So the first one is what? The easier one is the easier one is where? At the wall. And at the wall you have a no slip. Okay, so we'll write the first one. We'll have to integrate twice. So you integrate in y twice. You need two boundary conditions. The first boundary condition is the no slip at the wall. So u at any x y equals to 0 is equal to 0. And the second boundary condition, which is a bit harder, is what? Huh? No penetration where? But no penetration is going to give you a condition on u, and on which component of the velocity field is the no penetration boundary condition on v. Yeah, but v, actually if you wanted to know v, once you have u, you can compute v, because you know that partial u over partial x is equal to partial v over partial y is equal to minus partial u over partial x. Right? This is where you will get v from. But the no penetration boundary condition is going to be a boundary condition on v. So this is not helping you. I mean, where there's another physical process which you have to describe. Where is it? At the interface. Yeah. What boundary condition do you put at the interface? Huh? Stress. Yeah. So which stress is continuous? The shear stress is continuous. Yeah. Yeah. So what is the shear stress at the boundary? Yeah. So you have to impose your second boundary condition. This is very good. Is a stress boundary condition. Now, for you, is it going to be a stress boundary condition in the normal direction or in the tangential direction? Huh? So hold on. So at this point, maybe let's zoom in onto this interface, right? We are interested about the stress on this interface, right? So we have a normal vector. N is the normal vector to the interface, right? So the stress vector is T dot N, right? That's our stress vector. It has two components. It has one component in the normal direction, which gives you which you need if you want to impose a normal stress boundary condition, and a tangential component. Right? Which one do we use? The tangential, right? It should be clear that you should realize that you already used the normal one. The normal one is the one that gave you the pressure. You already imposed your stress boundary condition at the boundary in the normal direction. This is when you said the pressure atmospheric was the same as the pressure in the water in the paint layer right underneath the surface. Yeah? Is that clear? So here you still need to impose this here. So this is your tangential stress boundary condition. And so what do you write? You write continuity of stress. Yeah. I think we did that once before. So mu du dy in the water phase is going to be equal to mu du dy in the air phase. But what do you say at this point? Huh? Yeah, because the viscosity of air is really, really small. If you had a water-oil interface or an oil-something else interface where the two fluids are viscous, right? You may have to write viscosity in one fluid and match you may have to match the two tangential stresses, because you may still have to even solve for the velocity distribution in the other phase, right? But in that case, what is on the other side of the paint is air. And air is going to exert very little tangential friction onto the interface. Right? And I think this is also your experience. You don't think, when you see the paint, when you see slowly those little droplets form, you're not thinking, oh, the air friction is so strong, it's going to prevent that little droplet to fall, right? You're not thinking, and you're right not to think that. It would be great if you thought that in an exam as well, right? Because then what you would write is that this here is equal to 0, right? The friction from the air is going to be really small, so you almost have like a free stress boundary condition in tangential direction. Yeah. So your second boundary condition is, I haven't written in full, is mu du dy at any x and at y is equal to h of x is equal to 0. Again, if you are to write a boundary condition in your exam, I want to see this, because this is my stress. I also want to see where you impose the boundary condition. Right? If you just write that with no explanation, this is fine. I understand that you know what you're doing. But if you write mu du dy equals no equals to 0, or mu du dy equals to 0, but I don't know where you impose it, then I don't fully trust that you actually know what you're doing. Right, so just writing this here, writing this is enough. Here you have everything. Yeah. So once you integrate with those two boundary conditions, you get, let me write it here, you get u is equal to minus rho g divided by mu y squared divided by 2 minus h of x times y. Right, you can quickly verify that at y equals to 0, this is equal to 0, so this is my no slip. Right, now take the derivative of this, and here you will have y, and here you have h. So at y equals h, this is going to be equal to 0. Your first derivative is going to be equal to 0. Yeah. So just verify that. But this indeed satisfies those two boundary conditions here. The first one is here, and the second one is the stress boundary condition at the interface. Okay, and now once we have u, we can compute q. It's just this integral here. I have 10 more minutes, so I'm not going to compute. I'm not going to do it in front of you. So you find that q is equal to where is that? I'm getting lost in my own notes. Q is rho g h cubed divided by 3 mu. I'm actually not sure what it is. Okay, let me just do this integral then, because I'm not sure. So minus rho g divided by mu, and then I have to integrate. So this is y cubed divided by 6 minus h y squared divided by 2, and that is between 0 and h. So this is going to be equal to minus rho g divided by mu h cubed, and I have a 1/6 minus a 1/2. So I get a minus 1/3. So I have rho g h cubed divided by 3 mu. Okay, in principle this should be okay. Note that I have a positive number, which is a relief. The paint is indeed falling downwards. If you had a negative number, then you would know probably something went wrong in your integral, right? And the dimensions are fine. At this point, I would check the dimension, though I trust that they're fine, because here somewhere I have something which has the same dimensions. But if I were you, at this point, I would check my dimensions. Okay, so we have Q, and so now we can write an evolution equation from mass conservation, right? So I can write the equation for h, partial h over partial t, plus, and I forgot what q was. Q was equal to, can you remind me, there was a 3, there's a mu, an h squared cubed, what else? Rho g, and that's it? Okay, so partial q, partial x, so then this will be equal to rho g divided by 3 mu times, so I have a 3, so I'm gonna get rid of this 3, h squared partial h over partial x equals to 0. So this is very typical of lubrication. In any lubrication problem, when you're solving for the shape of the interface, and that comes in a lot in the industry, you know, going from surface coating applications to spreading of droplets, to Marangoni spreading, to anything, any process where you're dropping stuff and you have a liquid film which grows, you will have, so you solve for the velocity profile, and you put that into the mass conservation equation, and then instead of solving for the velocity, all you're solving for is a PDE for the height of your film. Right? So note that here, The only thing which is unknown, whatever we were looking from the beginning, when we're looking at our wall, is what is the height of what is the shape or the thickness of my paint layer. This is h as a function of x of t, and this is the equation that tells you how h changes. This is a PDE, which determines the evolution of the height as a function of time. It's a PDE in time and position x. And we're assuming that the flow is 2D. Of course, you know the flow is not 2D because when you're standing in front of your paint, you don't see. If I'm doing a cross section of my paint, right? You usually you see stuff like that, but those are droplets. So it's not like this entire bulging thing. What usually you would see, though, is droplets along an entire front. Right? You see that happens. And really, what this happens is that first, you destabilize like this, where you have this big, a big bulge that forms, and then you have an instability in this direction, which starts to form little fingers. Oftentimes, you may even see that you see droplets form a bit like this, right? So that here would be your initial bulge, and those are your little fingers here, right? Do you see what who has never painted? Who doesn't see what I'm? If you've painted enough, you would observe that. Next time you paint, just watch out for these. Now let's explain why you cannot avoid the formation of those droplets. So this equation is of the form of that equation here. Right? So if I assume if h was constant, right, then this term here would be a constant. Right? Let me call that C. Now how many of you have seen this PDE before? Yeah, so applied mathematicians and mechanical engineers, I don't expect you to know this equation. This is very close to this is very similar to the sound equation, or do you call it the sound equation? The wave equation. It's very close to it's one part of the wave equation, and the solution to that equation is a function of is a function like that. Right? A solution, if C was a constant, a solution H would be any given function f, say h naught, as a function of x minus ct. So those corresponds to traveling waves, right? Meaning that if my solution, if this is x and this is h, right? If at any time my solution was that, right? This is the thickness of my film. Now I flipped x, but this is the thickness of my film. Then my solution later on would be the same, but it would have translated at a velocity c. Okay? Now you don't need to know that, but this is just a mathematical thing. The solution to this equation is any function which just translate essentially as a function c, as a velocity c. Yeah? Is that? I'm not going to derive that for you. This, we'd see that in a math class. If you open Wikipedia, you'll find that. But just if you see this equation, just understand that what this represents is a solution, is a function which just translates with the velocity c. So if you know it at a given time, then you can infer it later on because you just take the function and you just translate it. Okay? Now this equation is a bit more complex. This equation here is a bit more complex than this one because it's nonlinear. It's nonlinear because this function, this c here, is not a constant. It actually depends on h. You see that? Yeah? So the important thing to note here is that c, the velocity at which you translate, increases with h. You see that? So the thicker my layer, the slower I go. The slower this part of the curve translates. Yeah? So let's say you start with a layer of paint and you are very happy, right? This is a few seconds after you paint it. Everything looks flat. You have none of those droplets. You're very happy, right? But then actually nothing is really flat. Things are not what it's like in the Matrix. Things are not what they look like, because in reality, you have little perturbation. It's not perfectly flat. Right? It's not perfectly flat. Yes? So it's not perfectly flat. Now from this equation, right? If it's not perfectly flat, but h is roughly constant, you would say, okay, c is roughly constant. So this little disturbance here, actually, let me say, let me make it a bit more. Let me start again because this is very unclear. So you think you did you think you did a great job and it looks very flat, but in reality, it's not so super flat. It's like this. Now, as long as h remains almost constant, c is constant, so everything is just going to translate down at the velocity c. Right? You can even compute the velocity c, right? Because c is, if h is, I don't know, 10 microns, you can just plug in the numbers, and rho, you know, for paint is maybe, I don't know, it's heavier than water, so maybe 2000, g is 10, mu is going to be, I don't know, 1 or 10 to the minus 1, and h is going to be, yeah, I would say probably 0.1 millimeter or 0.01 millimeter, so 10 to the minus, say, 4. Plug in the numbers, you'll get the velocity, and it's probably going to be on the order of, I don't know, half a millimeter per second, or probably less. You know, you would expect maybe 0.1 millimeter per second, something like that. Okay? So initially, everything, this whole profile, initially, just translate with this velocity c equal to rho g divided by mu times h squared. Okay. The problem is the following. This velocity here depends on h. Okay? So let's look at this part. Right? This is the part where you have less problems, because if you think about that point, right? If I think about this point here, the thickness h is a bit smaller than here. Yeah? So let's compare 2 points. I compare this point and that point. So here, the velocity is going to be a little bit slower than here. Yeah? So later on, if this point displaced here, right, this point will have displaced maybe over a slightly larger distance. Yeah? Because velocity is a bit larger. So that little feature here tends to get flattened out. So that's okay. The problem arises here. If I look at this little piece here, then note right here the thickness is larger, so the velocity is faster. So maybe it moved here, and right here the thickness is a bit slower, so the velocity is slower. Yeah? So maybe it will have displaced here. So that piece which was now initially relatively flat now becomes much more sharp. Do you see that? This is because essentially this equation in mathematical term is the hyperbolic equation, and what we're discussing is the phenomenon of shocks. Like your interface here, which initially is like that, is going to become more and more until you have a discontinuity, and that is because this point here is going to move faster than that point here. Yeah? So you cannot avoid those little droplets. They're going to happen. Right? As your film flows, whenever you have a slope which decreases, a decreasing slope, so when partial h over partial x is negative, then the slope will tend to increase, and that will create an initial bulge in the paint, and that bulge is going to destabilize in this direction, and then your little droplets form. Yeah? So if you had to design a paint, you would design a paint which dries quicker than that characteristic time scale for this instability to occur, or for that shock to occur. Yeah? Okay. So I think we've done enough lubrication problems. So on Friday I will start wave equations.